Yeah, please do so. It's very gracious of FRS to do that. So it's a big favor for you that you can have the software. Okay, we are coming now to the next chapter, chapter 4, and it's about market risk factors. Market risk factors, you could consider is, at least in the book, it's one of the most difficult part. You could consider it like that, because you can become very sophisticated, very mathematical there. And we could talk about it for days. By the way, I also expect some of you, at least some, if not all of you, to be better in that than me. So I think if you do quant finance and so on, you're definitely better than me. And so I'm not going to beat you, I'm not going to challenge you on this one. So if you want to challenge me, then I bring in another guy, so to have that level. Although it's important, it doesn't have the same importance here, and then I'm going to explain you why. Something else yet. For those who are not totally mathematically inclined, don't be too much afraid of chapter 4. So the test will only go into the depth as we discussed it about in the level here, in this lecture here. So that is about the level, what you have to understand. If you go to further level, you go to another class here. For the rest, basically, the book defines what you have to know, but in here we will be a little bit less deep, just to quieten you. So the overview of what we are doing here today. So market risk factors. Overview. So we will look at the different market risk factors. There's not just one factor. There are many factors. And then we will discuss important terms, because there are some confusions. There are too many terms, and how I understand them, and how we can understand them, and how are they related to what we are doing here. That's the second part. And then I will look at the different market risk factors, or modeling of those factors in different type of analysis, how they are important there. So we are coming to the market risk factor overview. So the risk factors are these red dots. And the special thing about them are that they are risky, meaning hard to project, hard to forecast. And with all your models you're doing, you have to stay quite humble and say, so everything is still on human scale. What we're doing, they are all models, and they are not very precise. For us, in this environment, as we think here, we do not care too much what kind of models you're using up there. We say, bring your model. Make it as sophisticated as you like, or as simple as you like. You can bring a stress model just from your belly, saying rates are going like that or this way. Or bring the most newest version, the multi-factor LIBOR market model, or any other forecast. We just plug it in. We take anything. And you will see in RiskPro, we have the LIBOR market model implemented. So it's quite substantial. There's something there. So, but you could bring another model if you say LIBOR market is not good. So we don't care. What we care about is what happens after a shock has happened, after a movement has happened. That is what we care about. So we care very much given a market risk factor. So how does it affect the financial contract and all the rest? That is our main business. And we have given you a good environment where you can do the sophisticated stuff as well. So no problem there. But the main question here is not which kind of models we are taking, so what is the effect given a model, given assumption, given anything. And the difference between them is here we are in a gray world, meaning so there's no true and false at the end of the day. You might have a very highly internally consistent model, where everything is fine and everything is consistent. But that doesn't mean that it is consistent with reality. It doesn't mean that it is a perfect forecast here. So, but given one model or one shock, the rest becomes mechanical. And we must remember the way we defined contract types. So we put everything into financial contract which can be considered certain. And what can be considered certain? There's only one thing which is certain in the financial market, which really comes to that close certainty. It's the financial contract, the promise of the financial contract, what you have agreed. And lawyers make sure that this is certain, that there should be no two interpretation. Still, there is sometimes, but that's going to be weeded out. For example, now there's a question, is Greek a default or not? So it's not, that is currently not, because it's a newer product, and it's a strange case. It has been constructed by politicians not to be a default, and still it's a kind of default, So there is now like a little thing here. But these things are normally weeded out as quick as possible. So the rest is certain. So the rest is certain that can be represented mechanically, can be represented by code. And that makes a nice architecture, of course. So we have the certain thing, and that's in the center. And that's not a small thing either. It's quite heavy what is happening there. So if you can model that part as certain, that makes the system quite strong. Special about market risk factors. Now, I'm focusing now on market risk, not on all risk factors, just on market risk, is that market risk factors have a double role, especially interest rate and FX rate. Interest rate and FX rate, they on one hand affect the expected cash flow. Think about the variable bond. So the rate of the variable bond is a function of the evolution of the market. And the same rates are used to discount cash flows. So if you have a fixed bond, market conditions play no role in determining the cash flows once the rate is fixed. So everything is only internal. But they still depend on market conditions due to the discounting. So the value, if it comes to value, etc., it's still there. So that makes things a little bit tricky. So this double interaction with the contract. The main categories of market risk factors, actually they are all, I think it covers it, from the financial market. First, yield curves, or interest rates, I maybe should say better. So interest rates, and there we have two types. One is the term structure, that's the yield curve actually. I think I should change a little bit the names there. So it's actually interest rate and then the term structure, which is the yield curve here. And then we have what we call product rates. Now, product rates are financial rates which follow somehow market conditions, but not really. And you have a lot of them. The main rate there is the saving rate. Again, very determinant for income. And of course, banks try to play around with it so that it's always in their favor. For example, if rates go up, you keep them low. No, then you go up. But no, we're under we're under liability side. No, when they go up, you keep them low as long as possible. And if they go up, and if they come down, you go quickly down. So that's what you do. So you play around with it, and it's somehow driven by the same factors which drive the yield curve, but not really correctly. So there's no elegant model. There's a lot of hands-on and thinking, but you have to think about, because your main profitability will depend on these kind of rates. So it's not something you can just disregard because it's not elegant. Now, real life is never that elegant normally, so it's the more hard questions which you have to solve. Then we have the FX rate. That's for all foreign exchange traded products, so you need an FX rate. Then we have the stock prices and stock indices, so anything which drives stocks as a risk factor, and then commodity prices and indices. So these are the financial risk factors we have to care about, and which are also correspondingly modeled inside RiskPro. You find those categories, and you have to have modeled for them if you have the products. For example, if in your model which you are building, you don't have a commodity, so you don't model commodities, of course. But yield curves, you always have to model FX rate, mostly. Now, some important, this what comes now is a little bit the collection of different terms. They're somehow related, but not fixedly related, but are important. They also partially overlap. I start with the St. Petersburg paradox. It's about risk neutrality. I don't know whether you know that, but it's an interesting paradox. I think it was by Bernoulli. I think he in St. Petersburg, he brought it up, and he invented a game. We toss a coin, and the payoff is 2 in the n minus 1 first power if the first n minus 1 tosses were tails. I explain it in a little bit in a different way. Let's assume you toss the throw and it is tail. Then we continue. If you throw again, it's again tail, we continue until the first head comes. So if the head, for example, comes first on the 6th throw, you have 5 tails and then 6th throw. Then it stops as soon as the head comes. So then we pay 2 in the 5th power. In this case, 32. So you get 32 francs. Let's assume I am the guy playing against you. So anybody can come and play. So we throw the coin, and I pay you 32 if it's at the 6th. I pay you, for example, 8 if the 4th row is there. 2 in the 3rd power is 8 if the 4th row is a 10. Now the question is, how much are you going to pay me in advance for that game? Anybody a bet? Anybody giving me, say, 1,000 francs for that I play? Who would offer me 1,000 francs to play one game? No? 100? Who would offer 100? No? 50? No? 20? Okay. Oh, bold. Good. 10? 5? Nobody. No, come on, 5 you're going to offer me for this game. 4? You offer me nothing. No, really. I mean, it's really because the test has been done several times. Is there somebody who would offer me at least 5? Nothing. 0. 2. 2. Okay, 2. 3. 3. Okay, something. 1. Who would offer me 1? Everybody. You know what you would have to offer me? What is the expectation value of that? Indefinite. 1,000 was very cheap, actually, if you would have offering. So why are you not offering? And you are students of, you know probability. Yeah, I think you're not like anybody who has no clue of that. And it always turns out, I think the average is 3 or 4 francs. That's about what the 3 or 4 units. If you go and ask that, so you're quite in the average here. So quite in the average here. Now, if you do the calculus, it's the sum of 1 to indefinite 2 minus 1 to 2 minus 1 ith power. So that cancels out. So you get sum 1/2 to endless. And you sum it up endless, you get endless. So it's endless. The expectation value is endless. So now, why are you not ready to give even 5 francs for that game? The reason is you are very risk averse. The risk aversion is very, very high. So you don't like games which pay sometimes a lot, but where you lose often. So that is basically what you're not ready to do. I think it's a similar observation. I don't go, but my son goes sometimes to Baden or something like that, and I think most people, they throw on color. It's like half, you get it back, if you put your money on a single number, so it's normally it's gone. But then you make a big gain every now and then. Although I think the expectation value of color and number is the same, I guess. There's only 1/37, which is, I think, in each case. So it's not the probability which makes it. It's the risk perception which we have. So what can we conclude here is that people are not risk neutral. And so you prefer more likely games, low payoffs, to unlikely high payoff game. But the bulk of theory of finance is in a risk-neutral setting here. So we don't care. So everybody would have given me endless, like millions for playing that game here. No, it's not true. And risk neutrality, if you look where this happens, actually it reflects in the market model somehow. You start tweaking around with that model, maybe a little bit to make it less neutral, for example. That's what you're doing. So it all plays in this market setting where you have this risk neutrality playing and coming in. So that was risk neutrality. So we take it all together. Another term is arbitrage-free. Actually, arbitrage freedom applies in cases where there is no real risk. That's a certain case. Because, for example, if you know you can buy gold here for X and sell it in the stock exchange in New York for X plus Y, everybody runs because people like that game. So if you're sure, everybody. Or it's the same like if you're in the shop and you have a butter which costs $2.10 and the other $2.15. Which one are you going to select? It's unfailable. You make arbitrage and you take the one, even if it's 1 cent, you take the cheaper. Or another thing, gas. People, you have a petrol pump which is 1 cent cheaper. The next one, people do go. They go and get across the. So arbitrage people like because it's a certain case. It's the no risk case here. So, but it also says there is no free lunch. So if there is really no risk, so then there should be no special gain. But still, you make sometimes. That's the little trick. You still can get a little bit out of it. And people do everything to get that little slice out of it. One very famous arbitrage condition is the one which we have written here, that these are rates. So if say R1 is the 1 year rate, R1, 2 is the 1 year rate in 1 year. That's the forward rate here. And the rule says that the one-year rate and the one-year forward rate must be equal to the two-year rate, because both are observable and both are tradable for each other. So there should be no difference, basically. And there is hardly a difference. So you even don't know which market is driving. Is the forward market driving the yield curve, or the yield curve the forward? It goes in all directions. So it's difficult to say where it is. And if it's certain the game is truly played, then people really play it, and you can calculate, and it's certain. Yeah, risk-free, we said already, where arbitrage is possible. Really, it's true arbitrage is only under risk-free conditions. And of course, in a risk-free world, risk neutrality applies because there's no risk. It's almost trivial here. But then often a risk-free world can be constructed, like with call put and so on. But still, then we will have some difficulties there, as we will see. Now, concerning expectations, we have a little bit like a continuum. So we have on one hand the risk-free world, the certainty, where we know what is happening. So this is the world we really like, actually. But then we have what we call risk, and then we have what we call uncertainty. It's a philosophical discussion, and some people say there is no distinction between risk and uncertainty, and some say, I prefer to think there is some difference. There are different levels, at least, of risk. So risk, I would consider that one which really happens in Baden or something like that, where you throw a dice and the dice is neutral itself, so you know the probability, and if you play it long enough, you get the expectation value. And you will then finally get your expected return here. And uncertainty is where you don't have really a basis of calculation. This goes back to Knight. That's an old doctoral thesis from, I think, 1929 or something like that, or 20s, far back here. And I think Keynes put it really well. He always had a good thing to say. By the way, he's a very good economist. It is safe to say that enterprise which depends on hopes stretching into the future benefits the community as a whole. But individual initiative will only be adequate when reasonable calculation is supplemented and supported by animal spirit, so that the thought of ultimate loss, which often overtakes pioneers, as experienced and undoubtedly tells us and them, is put aside as a healthy man puts aside the expectation of death. So there is something where you have calculation, and what we do here, basically, in this seminar, is mainly to bring that reasonable calculation, to push that a little bit further out. But we should have no doubt that still there you need an animal spirit on top. The entrepreneur which decides. They do a lot of calculation, and I have seen spreadsheets of how people calculate firms and so on. They are like 500 spreadsheets, and huge calculation. I have gone myself selling a firm, that kind of calculation. It takes you a year or two to calculate these things. So much probability at the end of the day. It's a very rough, a very bold decision, and this you still take. So I think we should do better calculation, especially where calculation can be done. It should be done. There should be no guessing about that. But still, we have that animal spirit which goes beyond that. And then the combination of arbitrage-free models and real-life expectations. That's an important distinction which we have to draw here. First of all, arbitrage-free forecasts are not unbiased forecasts. Just take the example of the rate here. So the two-year rate is equal to the one-year rate plus the one-year forward rate. So is the one-year forward rate a forecast? So this here. Where is the, okay. Is this a forecast? This one? Oh wait, this one. Is that the forecast of the 1-year rate in a year? And the answer is definitely not. Because, I still don't have, I can draw it into the air. Normally, yield curves are positively sloped. And if you apply that formula in a positively sloped, the forecast is always higher than today. You can, an easy calculation is, say, you have 5% today for 1-year rate and 7% for 2-year rate. So if this here, this is 5 and this is 7. So it's 107 square divided by 1.5. Must be something higher than 1.7. Otherwise it wouldn't get to 1.7 square, which is almost the average of it. So it's maybe 9%. So if you have positively sloped yield curves, then the forecast, you can derive a yield curve from that yield curve. A full yield curve into the future. That works. And you will see them in RISPRO. They're all there. So you can forecast the yield curve, but that means it's always rising. It's automatically, as soon as this is positively sloped, if it's negatively sloped, it's always falling. And if it's straight, it's basically straight. That's generally the rule which applies. So that would mean if you have positive sloped yield curves, you expect rising rates. Now, how many times of the real times yield curves are positively sloped? About 90%, roughly speaking. 90% of the time they are positively sloped. 5% may be negative, and 5% then neutral. So that would mean we would always expect rising rates. Do we do that? No, we don't do that. The reason is in the positive slope of the yield curve is most likely a liquidity premium included. So people prefer, if you are a house owner, you would like to have a long-term fixed mortgage. Surely, you know, because you have a salary, so that gives you certainty. You are even ready to pay some more for that. But if you have debt, you would like to give the money short-term. Because the money is the thing which you want to take and run, in the worst case. That's what it is. So it is a mismatch, and that's why the long-term rates have to be in tendency higher than the short-term rate. So although it's arbitrage-free, and it goes into all the calculation, it's not the forecast. So that has to be understood. So if you have all these problems of risk neutrality and so on, so how do we deal with that? There are two ways of dealing with it. So first of all, we know it's not risk neutral. So we have to somehow change something. So just by applying risk neutral thinking, we must be off. And the two rules are, you can either have risk neutral expectations of cash flows. That means you do the risk part already into the forecast of your cash flows. That means you become pessimistic. That's how you do it. So instead of going high, you go low. Say this is the risk-free case almost. And you discount that with the risk-free discount rate, with the yield curve which you observe. Or the other way around is do real-world expectation. So you say, okay, this is my mean and up and down, so you do everything real-world, and you discount it with a real-world rate. And the real-world rate has then some risk part in it. So the two methods basically are equivalent. It's like working on the denominator and on the numerator, but in reality, risk-neutral expectations are very difficult to obtain. So we will see when we do modeling of entire banks, the best is to make a real-world expectation of what you do, and then take, of course, corresponding discount factors which are included, which then express the risk part of it. And if you go and see how people buy firms, you know the discount spread is often 20%, 30%, you know, and this 1% of interest rate which you get now has no relevance even at the moment. So these are the possibilities. And especially if you do dynamic simulation within the workshop here, those who do dynamic simulation, so they should take that into account. So that the best is to do a real-world forecast as what you think. You have a good tool to do that, so that's easy. And then apply, if you do net present value calculation, apply the corresponding discount rate. There's another interesting example which shows how difficult risk neutrality is. So I think you're all aware with this SMILE problem. The SMILE problem says that if you are with the options, if you are at the forward, then the volatility is lowest. So this is the implied volatility we have here, and this is the at the moneyness. So if you're at forward, you're just at the money here. And as you move away, the implied volatility increases. That's something which shouldn't be, because you can create the risk-free case, and still people do not think like that. So that's why you have higher volatility. So what is the trick applied? You tweak the market conditions. You say, instead of going like that, you say, it goes like that. So you have more probabilities up there, maybe in the strike price, and so you get a different price. Which I, by the way, find an unlucky way of solving the problem. There would have been much, first of all, we have to tweak, that's clear. Somewhere we have to turn a screw and somehow bring it into close to reality. But what would have been more natural, the more natural screw we should have tweaked? Actually, the interest rate. Normally, the risk you have in the interest rate. And there is the interest rate in option pricing. And we could have used, you can use any variable, it's a choice. You could have even used time. I mean, it's a bad choice maybe, just to shorten or lengthen the deal. But from the two factors, interest rate and volatility, I would have chosen interest rate, because it would be in sync with all the rest. And now it's volatility. Why is it volatility? I think because it was more sexy. You know, everybody talking about volatility. It's more esoteric. And of course, there was big preoccupation with volatility when it first came up. So probably it was the thing which struck you first. So that was the parameter. But more natural would be actually having taken the rate. Okay, that's gone. So we have to be able to play it on both sides here. Yeah, so generally we have a calibration trick. As we said, now this, the SMILE is already a calibration trick. Just to extend, to increase or decrease the volatility, and so you get the price which you can observe. So you change the volatility that the observed price is equal to calculate the price. So we apply those tricks on dynamic models, and because dynamic models generally are fairly arbitrarily defined. I think the first condition for a dynamic model is that it has to be easy to handle mathematically. Oh, relatively easy. Still complicated enough that not everybody can follow, but still that you somehow can solve the problem. And there's usually one or more free parameter in such a function, and these free parameters are used for calibration. Just choose the parameter that observed world equal calculated world. That's what you basically do. And I already usually use the simple Wasicek model. So there you have two parameters even, A and B. So you always find a kind of world which comes close to your observation here. Yeah, so these things, you have to just to know, consider, think about it. So in which case are we? Are we risk-free? Is there risk? Did we apply a discount factor? Yes, no, do we have to? Etc., etc. It's more an art. It's know to choose the right thing at the right moment. Now we look at market risk factors in different modes of analysis. And modes of analysis, I mean this. We had it already once in the first lecture. We said there are, here we made 5 types of analysis. That's a little bit arbitrary. You could probably make a different, but because we normally have no static dynamic, but there are so many intermediate stages, so it's better to have at least 5. You might make even more of them, but I think that gives you a good overview. And these are also the models we are doing here in the seminar. So let's go to 1. So with type 1, I mean this here. Expected behavior, expected market. So everything nice and easy. So we have a yield curve, its derivations. And for you to know also inside RiskPro, there is always, the outside curve is normally a coupon-bearing curve. So as you observe it in reality, like the 1-year rate, the 2-year rate, the 3-year rate, like the swap rate. And that is turned then into a zero coupon curve internally. And actually, day-count methods play a role as well, actual. And then it's turned into discount factors and forward rates. That's how it works. Huh? So you have an outside observed world of interest rate. You go back to a zero coupon, and then to discount factors. By the way, are you aware why we need zero coupons? Is that what is the advantage of zero coupon rates versus coupon bearing rates? The advantage is you can basically then generate the cash flows and look at each cash flow like a zero coupon. So you don't have all the problems of reinvesting and all the thoughts which come in between. So that's why you need the zero coupon as a first step. Very helpful. These are good ways of dealing with the problem. Now, if you have that, this is sufficient to work in a risk-free world, so to a risk-neutral world here, and linear instruments. So in linear instrument and no risk, so then you apply it straightforward. You generate the cash flow, you use these discount factors, and you discount. But then we have some instruments where this doesn't work, and these are all option-related instruments because they are non-symmetric. So you cannot deal with it just by discounting expected cash flows. So you have to weight them as well at the same time. So that makes it more difficult here. But if you have this static and there, we have like 2 versions. In the black shoals, you are dynamic, but it's an analytical solution. So you can almost treat it like static. the VAR, the volatility is... So we treat that as case 1. But here you see it's a little bit arbitrary, whether you make an additional category. Also, parametric VAR is like a case 1 case because it's all just analytic. So you will see that yet, how that works. These are border cases. Yeah, yield curve. I think we said already all that. But this is good to know how we deal with the yield curves inside RiskPro. So we have, as I said already, we have the zero and the coupon bearing rate. So what you see outside is mostly coupon bearing rates, so which have a coupon included. But then you can always go and look at the zero rate with a little toggle. You see the zero rate. And then we have forward rates, and the calculation is always like that. So the forward rate at T0 for the period T1 to T2. For example, today, the 3 to 9 months. So it's a 6 months forward in 3 months. So then T1 would be 3 months, that would be 9 months. So it's a 6 months stretch forward here. So that is the calculation you do. So you take the coupon rate for 2 and at a zero coupon rate for 2 periods, and then at now and for the second period, and you divide by the time difference. And here you multiply with the time. So it's a very simple calculation. So once you have brought it down from coupon bearing, zero coupon, and then continuous compounding. And here the short rate is just then if you let this go to zero, the difference here. The short rate is just for a second, in today or in 5 months or in 1 year here. And other way around here, the forward rate from T1 to T2 can then also expressed as the integral of the short rate from T0 to, that's just the other way around. Or the rate T0 to T, for which we had it already, is like the integral from T0 to T. So that's all related, and it's always good to know. But at the end, you get the discount factors nicely on the timeline, and they're all consistent. That's the good thing. Okay, so that was all about type 1 calculation. So you have a yield curve, you have the forward rate, you have all that, you have cash flows, and you discount them. And you do VAR calculation and maybe simple bond, option calculation. Type 2 is now this here. Okay. It has because if you go back, so what we have here in type 2 maybe here is shocked market and shocked behavior. So we shock risk factors actually here. So it has much similarity to type 1 because the initial position can be calculated with the actual market conditions. Then we apply a stress and then we recalculate the condition. That's all we do. Or stressed VAR is something similar. So where you have stressed the initial conditions, you stress the volatilities also, and do another. So stress test, how do they work? I think we showed that already in the first lecture. So it's an arbitrary shock of risk factors. What are the risk factors? These are the risk factors here. Market, we talked just about market, but these are risk factors as well. And the market stress is nothing else than taking this current position, using yield curve, forward rate calculation, zero coupon, etc., calculate the value, stress the yield curve, recalculate. In credit risk, it's using the current rating, stress it, downgrade, and recalculate. And for a typical liquidity stress, they happen often here, not always, but that's a classical one. Because, for example, this is the drawing behavior of the saving account owners. So they draw, if they're not afraid, they keep the money with you, they roll it over, so not dangerous. But if they get doubt about you as a bank, so saving accounts are sucked out of the system, you can keep it back for a while because there's some legal conditions which allow you, but maybe you still have, this will be the drawing. And so it will take out all the liquidity of the system and then you will see that. So this is what we call type 2 calculation. Type 3, so we have now here in type 2 we were still static, real static. So although we shifted something, but it happened in no time. It's like comparing two cases in no time. Okay? So we are talking on the topic of type 3 analysis, and type 3 is very important if it comes to option valuation, especially non-trivial options here, because we have unsymmetric payoff. And so we have to model that often with just dynamic markets. And in RiskPro, you will find the LIBOR market model, which is doing that, and Monte Carlo as a general method where you can do the dynamic and then price according to whatever the rule is. And of course, we should never solve with Monte Carlo what can be solved analytically. Because it's a cost of about this factor 1,000 or something like that. So try to solve analytical what you can solve analytical. Yeah, so that is what's happening in the background. If you do type 3 analysis, you run just processes into the future, and you have a certain probability distribution across the time over here. Yeah, if you have a model like that, especially in the interest rate model, you have to know they are a little bit special. So there is the condition of positivity. Normally the rate should be bigger than 0, which maybe something also not holding true all the time. Mean reversion, that's a very special thing. So FX rates or stock markets, they can go anywhere. And interest rates, they are somehow bounded, at least as long as you're in a healthy economy, you know, so it's between maybe 0 and 20%, where normally the rates reside, and that's over long history, very long history. Yeah, there is volatility term structure is included in RiskPro, so we have the full term structure of volatility here, and it's traceable. Yeah, the LIBOR market model, it's an arbitrage-free term structure model, and we have 2 calibration inside, one to the cap floor and the other to the swaption. You can always calibrate it to anything in model, and as good as you calibrate it, as good your pricing becomes. Basically, you can calibrate it for every single instrument. But is that a good idea? Maybe for pricing a single instrument, maybe, but our idea is to get a full picture of the full bank. So we rather should have one common underlying model for interest. That's much more. And then the deviation, look at the deviation of it. So while it's good for pricing a single instrument to calibrate as much as you can, it is not good if your target is to oversee the whole bank. So it's better to assume there is one common underlying movement to calibrate on that and then see how they deviate. So, and thanks to these calibration techniques, because you can calibrate it individually, it's much used in the option. And it's consistent with Black-Scholes. But we have to see already if you have the 2 versions to calibrate it to the cap floor or to swaptions, we have already an inconsistency in the system. So which one of the 2 is true? Which one you apply in which case? Especially since we apply it in terms of analogy. So we have to price something. So we go to that market, calibrate it here, and apply it here. So there's always some problem. But it's very widely accepted, LIBOR market model. So you can work with it. Type 4, we are not discussing. That's a little bit portfolio optimization, something we don't discuss. So, but then type 5 here, that's then the real dynamic part. While in type 3, we just moved the markets into the future, but we kept the position at the present. So we had something dynamic in the market, but we were static really in the portfolio here. So in dynamic, we will go with the portfolio into the future as well. Then, of course, here, if you are dynamic, the forward rates are really a bad forecast. You shouldn't use forward rates here. So what you need more are real world models. And what are real world models? A real world model is the model a typical economist would construct. And so what does it take into account? The money supply, mainly, maybe inflation in the rest of the world, and things like that. Are these models highly reliable? No. But do we have something better? No. So you have to do the best. You have to do the best. And sometimes belly estimation, a belly feeling is not that bad, so you might have the right feeling. So, but if you do real world models, there are 3 ways of doing that. One is simple what if. Just take what you have and somehow forecast it according to your feeling. That's like stress test, but now going more into the dynamic, into the future here. Or historical scenarios. Just pick out a history and apply it into the future. That's often like historical backtesting and so on. It's a good method. So you have historical cases and you see, could I survive these cases? Or then historical Monte Carlo. So Monte Carlo, they need a mean, a variance, a mean reversion, and the mean itself could be a historical scenario, or could be a what if, whatever. If you think this time the forward rates are a good forecast, sometimes they are. When the rates change, normally then they are, then you can take that. But the main thing is there to take the economic knowledge into account. Yes, and then what you have to add, so this is what you often do, you derive a model in one market, and then you apply it to something else. That's basically what you do if you do fair value valuation. You go into the traded bond market, for example, and then you apply it to your loans. It's done. And I think it's something reasonable. But then you have to work with spreads. Now, so if, for example, you derive it in a risk-free bond market, wherever this exists, or half risk-free, and you apply it then to your loan portfolio, you have to add spreads. And the spreads then will calibrate it back, the bond portfolio, to your loan portfolio more to reality. And spreads, of course, are a little bit depending on the rating. And then, of course, if you have a loan portfolio, you don't really have a rating, so you only have an internal rating, but so then you have to match somehow the external rating. And so you see, it's a lot of art. By the way, that keeps it interesting. So it doesn't go down just to pure mathematics or pure engineering, which is also an interesting part, but the management part is still a choice, the right choice. So nothing will ever, I don't believe, we can ever do away with that. Another problem you have to solve if you are, say you model a bank, a retail bank. So a retail bank definitely will include some saving accounts. So saving accounts, the rates depend on the saving rate. And the saving rate is one of these not so nice product rates because it behaves a little bit like markets and it partially not. For example, here, that could be a rule that's arbitrary. That's very arbitrary. Other rules could apply. So the saving rate in T plus 1 is the saving rate in T1 if the rate, let's say if the 1 year market rate hasn't changed more than 0.5%. That means, so saving rates are sluggish, they're slow. And so if little movement in the market, you get no movement in the saving rate. But this is only an example, so it's not that model. I just want to give you an example here. But then you could say, and it is, say, it is saving rate T1 plus A times the difference between the two on a factor as A. That means we adapt a little bit. A will be then most likely less than 1 because we adapt less than the market conditions. Or depending whether we go up and down, we have to, yes, that's exactly here the case. If the rate goes up, No, if the rate goes up, then A is less than 1, yes. And then the other thing, if the rate goes down, then it's B times, and B is probably bigger than 1 because we try to go fast down with the rates. So that is a model of your own behavior, how you adapt rates. Somehow there is a forecast because it's you as a bank who decides to do so. But of course you do not do it fully on your own because you have competition. So it's art. So they are important. So if you model things like that, you have to model a saving rate as well. That's another way of discussing arbitrage-free versus real-world modeling. So that's the full model as we have it. So here we have our investment horizon, and here we have natural time. So if you do dynamic simulation, we go along this timeline and do deals always in this direction. That is what we do. And in this direction, normally you work often with arbitrage-free models because you have some comparison with some other models. And if you go in this direction, so the market forecast is a real-world model. So not just a forward rate model or something like a forecast of what you ever think, what your economic sense tells you how to forecast. But then if you go in this direction, like here, and do a valuation here, then you do again an arbitrage-free model there. So at any point you can stop, you can take the condition which you have forecasted then, and apply the forecasted condition on an arbitrage-free thinking on the position. This calls for parallel valuation techniques. So on one hand we have arbitrage-free models all the time there, and this has to be mixed with real-world model. So it needs a strict separation of cash flow generation and discounting, which often is not the case if everything is meshed up in one formula. So it's not so easy to distinguish. Yeah, that maybe brings us to the end, and Yanis needs some time for you concerning the model. Here we try to give some systematics of what kind of technique can you use? When are you in an arbitrage-free world and when not? When are you in a real world? So here, if we have, the question is there an active liquid market? That's the question. If it exists, here then we go down here. Then the next question is, can risk be fully hedged? Fully hedged means each risk factor in the system. So don't we have basis risk? Can we really, do we have the market itself? That's basically the question here. So there's a unique risk-neutral probability, because then we can derive the risk-neutral probability because the risk is priced into that market. And if that is yes, yes, then we have risk-neutral valuation. So here we are in a very good world. If no, then the next question is there an additional market for additional risk sources? So can we go into a similar market and get the risk sources there? If yes, then we calibrate that model to that risk and do calculation. If no, then the next question is, are the non-traded cash flows small? Regarding to wealth, that means non-traded cash flows are your personal cash flows, like from your firm, and traded would be the ones which are in the stock market and so on. If they are small, that means you have, if yes means most is in the stock market, so then this is a possible solution. You use the World Capital Index for discounting. So there's a special theory about it. If no, then you are in this case here. And that's the same case like coming from up here. So there is no active market. Arbitrage-free pricing is not possible. So you can only use real-world cash flows discounted with risk-adjusted weights. And that is the case where we are in many of those models. The model we discussed before, that's definitely something like which you have to treat on this scale here. And everything is possible, and we have to know that most of the university is probably over here. I assume so. Reality is more here. So we have the possibility to discuss and describe reality here more. And we have to know this world is very small and this world is very big. This is most of the things we do happen actually in this world. And maybe we're a little bit in between. So we do have comparisons. We can take some conclusion from another market, etc., etc. And we apply it as our feeling tells us. Yes. So far to markets. And for you, it will not be really difficult. So the software is there. It's the setting of the parameters. But what we need to is to understand in which state are we. So what are we really doing? So here, I think the philosophical questions are, at least for this lecture, more important than the technical questions, the real derivation. Yeah, Yanis.